So we're going to go over the solar system. So on your desktop right now, or split screen on your iPads or wherever you are, you should have your reference table open to page 15. I'm going to give you guys a bunch of information on here, but you're not going to have to copy it all down because, again, a lot of the information is already on reference table page 15. All right, so if you're following along, we're on review book pages 45 to 47, right, which you guys are all following along anyway. All right, so here's the reference table. The reference table has the distance from the sun, right, in millions of kilometers, the period of revolution in days or years, the period of rotation at their equator, their eccentricity, which is basically going to give us how far off of a perfect circle their orbit is. Remember, none of the orbits are actually a perfect circle. They're slightly oblong, okay? Their equatorial diameter, or how big their diameter actually goes all the way around. Their mass in comparison to Earth. So Earth is going to be obviously one Earth, and then Jupiter is 317.83 of those Earths, all right? It also gives us the density in grams per centimeters cubed. That's a lot of information, but none of it you have to memorize. The other thing on here you want to notice is Neptune is the last one. Pluto is not listed on here. Okay, they are listed in order from closest to the sun to furthest away, except for obviously Earth's moon because it's not part of the main planets of our solar system. Okay, so there's just some things to keep in mind when you're looking at this reference table. All right, so what are the components of the solar system? Well, the solar system is going to include, all right, the sun, like we were talking about yesterday, which is a medium-sized star, okay? It's medium-sized and it's middle-aged, so it's halfway through of its life cycle, okay? And it's not a large star. It's a medium star, believe it or not, okay? The 8 planets and their associated moons. We do not include Pluto anymore now that it is a dwarf planet. And I'm going to show you why as we go on. Okay. Asteroids, which are chunks of rock that are, there's an asteroid belt that separates Mars and Jupiter, which actually will end up being easier for you to tell the difference between the groups. Okay? And comets. They are massive frozen gas and rock together. Okay? So when we're talking about our solar system, we're going to be talking about these specific parts. Okay? You guys ready? Or you need a minute?
Not yet.
Okay, let me know when you're done, okay? Now, we are going to go into detail about all of them. We already went through the sun, right, for the most part, right? You got to watch the video when we were talking about fusion, right? Are we good?
Wait 1 second.
Okay. Okay, so now we have to talk about the formation of the solar system. All right, it's the formation of the solar system happened about 4.6 billion years ago. Okay, where a large cloud of gas, ice, and dust, that was all that existed at the time. It's basically space crap. Okay, you had some gases, you had some ice, you had some space dust that existed. All right, so just like when I showed you the video on how the moon was formed, right, the stuff that's out in space came closer together, and when they start to slowly rotate, they start to get what? Do you guys remember? What do they start to form when they start to rotate? Right, they coalesce. What do they get when they start to rotate? Starts with a G. No? Nobody? You guys haven't been studying? Gravity? You guys don't remember this? Right? So when they contract and they start to slowly rotate, they form gravity. When they form gravitational pull, then they're supposed to pull more stuff in, and then they rotate faster. Right? When they contract, you're going to increase the density because now you have more stuff together, right? Which means there's more of a gravitational pull, and they're going to rotate faster, right? Again, gravity begins to pull towards the center, right? Density increases, you increase rotation and gravity, right? Notice the theme. When they start to contract, they rotate. You increase the density, you increase the rotation, you get more gravity. The more gravity, you get to have more density, you increase the rotation, you increase the gravity. Notice the cycle, right? The more density of a system you have, the more it's going to rotate and the more gravity you're going to have. Okay? Okay.
Can you go back really quick?
That's why I said, guys, you got to answer me. Can't see you right now, so I don't know if you can go. It's not like when we're in class and I can see you guys. Okay, so once that happens, you start to form a disk with a very large center, okay, which you'll see in the video, right? That central mass, that center, starts to heat up due to that contraction, because what's happening is as you're pulling things in, you're increasing the gravity, you're increasing the density, you're increasing the rotation. The faster they go, the hotter they become, okay? The temperatures themselves reach about 10 million Kelvin. Okay, that is extremely hot. Now, remember what I told you the other day, or I told you yesterday, right? Fusion needs heat in order to happen. So as this central mass starts to heat up, because we're contracting all this stuff together, we're throwing them together, they're spinning around, right? And the temperatures are increasing, we're setting this up so that you can have the process of fusion. Okay, those beginning hydrogen atoms begin to have their nuclei forming into, right, they start to fuse together, forming into helium, right? The nuclei of the hydrogen atoms begin to fully become together. They're forced together because the hydrogen atom's nucleus and another hydrogen atom's nucleus are both positive. So it's just like taking two magnets. You have to force them together. By having them under extreme amounts of heat and pressure, you can overcome those forces and put them together to fuse together to become a larger element like helium. Okay? So fusion's going to keep happening, which then forms our sun. So that's going to be our center, right? That's the central mass that began to heat up and fuse together, right? Then you have all the rest of the stuff around it. The rest of that stuff in and of itself basically coalesces and becomes the planets that we know today, right? So they are going to come together slowly. They hit into each other. They start rotating, right? They increase their rotation, which means that their density is going to increase, which means that their gravity is going to increase until eventually you form the planets. When I show you guys videos, is it easier if I mute myself? Like, do you hear an echo?
Yeah.
Okay.
So like mute the one that's showing you.
So mute the camera or mute the actual video?
Like mute the account that you're on right now, the one that's not presenting.
Okay. Okay. So it's a commercial.
Chromebooks are a new way to laptop.
No, we can't hear.
No. Work this.
All right, so this has to stay on then.
It yesterday didn't have an echo when you were muted, so I
The
think
story
it's
of our Earth's formation 4.5 billion years ago, and of a little asteroid called Bennu, who has also survived until now. We have the team at NASA to thank for bringing us this video. The Milky Way, home to billions of stars, rising and setting over billions of worlds, including our own. In this vast expanse, how did our sun, the Earth, and the planets come to be? In recent decades, our understanding of the solar system's evolution has greatly improved, but deep questions remain. To answer those questions, astronomers are preparing to visit someplace very small. Asteroid Bennu. A lump of rock and organic material, the early building blocks of the solar system, of Earth, of us. Bennu is a time capsule, and its journey takes us way, way back, 4.5 billion years. The raw ingredients of Bennu and our solar system originated in a stellar nursery, a vast cloud of hydrogen, helium, and dust. Our own sun doesn't yet exist. Nearby are hot stars like this one, quickly burning up its fuel and destroying itself in a colossal explosion called a supernova. The explosion destabilizes our cloud, causing it to collapse. In the geologic blink of an eye, 100,000 years, gravity and angular momentum flatten the cloud into a swirling disk. In the center, where molecules crash together tightest, a protostar revs up to incredible pressures and temperatures. Deep within the disk, clumps of dust not much larger than a grain of wheat are flash heated into droplets of molten rock, called chondrules. The source of this heat remains a mystery. Chondrules are destined to become the building blocks of the solar system. Coaxed by gravity and turbulence, the chondrules clump. They grow into the first asteroids, into mountains, into planets. The asteroids are rubble piles of rock, metal, ice, and organics. This large asteroid is the parent body of Bennu, a protoplanet whose size we can only guess. Closer to the protostar, a planet begins to form. And then, dawn in the solar system. the protostar undergoes fusion and ignites, revealing our sun. But the solar system is far from finished. Jupiter most likely forms near its outer edge, but just 500 million years after the sun ignites, some believe that it slowly moves inward. Its massive gravity ripples the asteroid belt, disrupting countless asteroids and comets, flinging them toward the sun. They rain down on the inner planets, hammering and remelting large portions of their crust. Did these impacts also deliver organics and water, key ingredients for life? Back in the asteroid belt, Bennu's parent body is lucky. It survives this period of heavy bombardment. The solar system cools and calms. Jupiter and its many moons assume the orbits that we see today. Billions of years of quiet follow, more or less. Then a billion years ago, one theory suggests a collision shatters the protoplanet. Some of the debris loosely coalesces into a new, smaller body, Bennu. But Bennu will not stay in place. Dull, non-reflective, it slowly migrates toward the sun. Solar heating turns its warm side into a low-intensity thruster. Through millions of years, Bennu's orbit gradually tightens until it interacts with Saturn's gravity, altering its trajectory and hurling it into the inner solar system. Close encounters with Earth and Venus follow. Their gravitational tugs may have repeatedly stretched and reformed Bennu, turning it inside out and pulling off loose material. As a result, it has no satellites of its own, until now. Today, NASA is sending a spacecraft called OSIRIS-REx to explore Bennu and retrieve a sample. Why? Bennu has survived its long journey and settled into a near-Earth orbit, bringing its secrets within our reach. Now it is ready to teach us more about the solar system's history, its formation, its evolution, and our own place among the stars.
All right, so you can see there that how fusion, when it happened in the sun, right, it shoots out all that energy, right? So, am I still muted? No, right?
No.
Okay.
No.
No.
Here are the steps, right? We started off with a big dust cloud with all that other space stuff in there. They start to rotate and revolve as it starts. Well, actually, as the sun in the center starts to rotate, right? Everything else starts to revolve around it. Then through the process of fusion, you start to get these paths that start to happen. They get, this is just the leftover gas and the space stuff, space crap that's out there, right? As they come, they coalesce and they come closer together, you can see how they're more defined. That stuff becomes our planets that we know today. If you look up, there are no lines that show us the actual orbits like this. It doesn't exist, okay? But that's how they are formed, all right? So if you look, right, all of the inner planets are revolving super fast around the sun because their orbit is super slow, right? If you look at the rest of them, the orbits are super small, right? The rest of them, because their orbits are so large, right, they are moving super slow in their orbits, which means it'll take them longer, right, than a year to go one full revolution around there, okay? Right? So this gives you a little bit more of an idea of what the orbits are. Notice that they are not perfect circles. They're kind of elongated a little bit. And they're not all exactly the same. That's important to understand. All of the orbits are not exactly the same size. They're not going to be the same size. Okay. Also looking at this, you'll notice that this is part of the reason why Pluto is no longer an official planet. Because one of the requirements in order to be an official planet is that you are not you are not influenced by any other orbits around you besides the gravitational pull of the sun. Notice how Pluto's orbit actually overlaps Neptune's. The theory behind this is that Pluto is actually being influenced by Neptune, and now they're saying also that there are some planets outside of our solar system that do not revolve around our sun that might be influencing Pluto as well. So that was one reason why they decided to make Pluto a dwarf planet and not officially part of our solar system. They're actually starting to think that it at one point was a moon for another planet, but they've disregarded that to them for the most part. Okay, so how are these planets going to move? All right, they're going to move on the same plane. That's that imaginary flat surface, right? So if you're looking here, right, we have this x-axis. They're pretty much all on the same plane. Now, depending, just like the moon does for us, it might be slightly off. Okay? And this is review of pages 49 to 50 for those of you who are following along there. Okay, so when we had that whole Big Bang that happened, right, you started off with the sun was created in the middle, and then they all kind of flattened out from there. Okay, I believe you guys should have this on PowerPoint pictures. If not, remind me and I will post them today. For now, if you'd like to take a screenshot of this, I highly recommend it. Okay, it gives you the tilt of each of the planets. Okay, and it also shows you how their orbits are. So another reason why Pluto was basically shown as not a planet in our solar system is because look how far off that its orbit is compared to everybody else's. Right, off of that x-axis, Pluto is 17 degrees off, so it's extremely tilted. Mercury is 7 degrees off, but that's being influenced by the sun itself, so they don't really see that as a problem. All right, so a couple of things to notice. The reason why they keep looking at the planet Mars for life is because it has a lot of things that are very similar to Earth, right? Its tilt is 25.2 degrees, so that's only 2 degrees more than we already have, so it should have seasons, right? When you're looking at it, right, it's a little bit smaller, which means that we'd have to deal with that population loss. But at the same time, there's not really anybody who's living on the ocean of the Earth. So you take it and you leave it when it comes to that. A couple of other things to point out, like Venus is completely upside down compared to where it should be. Uranus is sideways. Neptune is also tilted about the same as the Earth's. All right. You're responsible for knowing the order, but again, it's on the Earth Science Reference Table. So the way that I remember it is my very educated mother just served us nachos, because we don't include Pluto anymore. Okay, so it's my very educated mother just served us nachos. Because I might ask you to do this without your reference table, and you'll have to know. Okay, you'll have to know what order the planets are in. So it goes Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Okay. All right. So, right. Again, they're almost circular orbits, but they're not 100% a circle. Okay, which is what we call an elliptical orbit. This is an ellipse or an elliptical orbit. Okay, how far off they are from a perfect circle, you're going to learn how to determine. Okay, just like everything else, they're revolving counterclockwise. Right, and they're also, for the most part, rotating counterclockwise, with the exception of Venus, Uranus, and Pluto. Okay, those are rotating clockwise. Okay, you guys good?
Wait.
Okay.
I'm good.
Good. Okay. All right. So we said that Mercury was about 7 degrees off and Pluto was 17 degrees off. Pretty much every other planet will only have their orbit changed a little bit by 3.4 degrees, I think is the max. Okay, except for Mercury and Pluto, which is again another factor against Pluto. Pluto's kind of the odd man out. Okay, you'll notice that as you get further out, once you get past Mars, all of the planets are much larger. They're made up of similar things. And Pluto does not fit that category, which is again why they've been saying that Pluto is not a planet. Okay, so let's talk about those orbits. Right, you already know what revolution is. You don't need to write it down again. Right, an orbit itself is the actual path that is taken by that object that is revolving. So it's the predictable pathway that the planets will stay in. And remember, they stay in that orbit because of that mutual gravitational attraction between the sun and the planet and the sun. Okay, so they're both attracted to each other at all times. So they stay there for that reason. Okay, like we said before, celestial objects have elliptical orbits, right? They are not a perfect circle. I want you to make sure you know that, highlight that, star that, do what you got to do, okay? It's also part of the reason why that at some points we are closer to the sun, even though it's winter, and some points we are further away from the sun. There are some points that the moon is closer to us, so it looks bigger, right? And there are some times where it's further away from us, so it looks smaller, but the moon's size did not change. Okay, so we have to talk about the law of planetary motion. All right, so the first law is that the planets are going to move in elliptical orbits with the sun at one focus. So the focus is going to be the foci should be are 2 points that are inside of these elliptical orbits. All right, guys, the time is up, so this is where we're going to end today. I want you guys to stay safe. Remember your rules for social distancing and everything else. Please stay safe, guys. I don't want anything bad to happen to you guys. All right, have a great Thanksgiving, and I will see you hopefully on Monday. All right?
Bye.
Happy Thanksgiving.
Bye.
Happy Thanksgiving.